All righty. Let's begin with the physics section, physics side of things. Mechanics. That's the first section. And we're looking at units of measurement. And here's the introduction. Oh, and that looks like a whirlpool galaxy. This image might be showing any number of things. It might be a whirlpool in a tank of water, or perhaps a collage of paint and shiny beads done for art class. Without knowing the size of the objects in units we will recognize, such as meters or inches, it is difficult to know what we're looking at. In fact, this image shows the whirlpool galaxy and its companion galaxy, which is about 60,000 light years in diameter, about 6 times 10 to the 17 kilometers across. Okay, well, 60,000 is 6 times 10 to the 4. And making the division here, that would mean that a light year is about 10 to the 13 kilometers, or about 10 trillion kilometers. And there's the credit there. Let's see. Okay, there are the learning objectives. I don't really like to read those so much. I like to just dive in. The scope of physics. Take another look at the chapter opening image, as we just saw it. The whirlpool galaxy contains billions of individual stars, as well as huge clouds of gas and dust. Its companion galaxy is also visible to the right. The pair of galaxies lies a staggering billion trillion miles. Notice how they use MI, and billion trillion is indeed 10 to the 21. Billion is 10 to the 9. Trillion is 10 to the 12. We add the 9 and 12 and we get 21. They're both a billion trillion miles from our own galaxy, which is called the Milky Way. The stars and planets that make up the whirlpool galaxy might seem to be the furthest thing from most people's everyday lives, but the whirlpool is a great starting point to think about the forces that hold the universe together, the forces that cause the whirlpool galaxy to act as it does, and are thought to be the same forces we contend with here on Earth, whether we are planning to send a rocket into space or simply planning to raise the walls for a new home. So what force are they talking about? It must, of course, be gravity. The gravity that causes the stars of the whirlpool galaxy to rotate and revolve is thought to be the same as what causes water to flow over hydroelectric dams here on Earth. It's very good how they're laying out that assumption on the table, because it is an assumption that there are forces at play a billion trillion miles away that operate under the same laws as here on Earth. That's an assumption. When you look up at the stars, realize the forces out there are the same as the ones here on Earth. Realize the forces out there are the same as the ones here on Earth. Okay, I don't like that, because that's like telling you, it's like commanding you to just accept the assumption rather than just say, okay, acknowledge that we do make that assumption. Through a study of physics, you may gain a greater understanding of the interconnectedness of everything we can see and know in this universe. Humans have created and manufactured millions of different objects. I just read last night, for example, that there's over 1.6 billion cars in the world, for example. And the number of transistors, it's some stupidly huge number. I forget how many zeros it is. Successive technological periods, often referred to as the Stone Age, the Bronze Age, the Iron Age, and so on, are marked by knowledge of the physical properties of certain materials and the ability to manipulate them. Not everybody accepts this tripartite division of history, but I do understand why they're raising it here. It's just an example of the kind of what objects that we can manipulate, the materials that we can. This knowledge all stems from physics, whether it's the way a rock would flake when constructing a spear point, that's for the Stone Age, the effect of integrating carbon with iron in South Indian and Sri Lankan furnaces to create the earliest high-quality steel. Okay, that's sort of referring, is that referring to the Bronze Age then? Or the proper way to combine perfectly ground and polished pieces of glass to create optical instruments. Our current technological age is called the information age and can be traced to critical innovations made by people from all backgrounds working together. Muhammad M. Atala and Dawon Kang, for example, invented the MOSFET, metallic oxide semiconductor field effect transistor. Metal oxide semiconductor field effect transistor. Metal oxide semiconductor field effect transistor, MOSFET. Although unknown to most people, this tiny device created in 1959 by an Egyptian-born scientist and a Korean-born scientist working in a lab in New Jersey in the United States is the basis for modern electronics. More MOSFETs have been produced than any other object in all of human history. They're used in computers, smartphones, microwave ovens, automotive controls, medical instruments, and nearly every other electronic device. So right now I'm looking at my phone and there must be millions of them in there. Next, think about the most exciting modern technologies that you have heard about in the news, such as trains that levitate above tracks. Oh yes, the maglev, I've heard of that. Invisibility cloaks that bend light around them. I think I saw a YouTube video about that once. And microscopic robots that fight cancer cells in our bodies. I've never heard of that before. All these groundbreaking advances, commonplace or unbelievable, rely on the principles of physics. Aside from playing a significant role in technology, professionals such as engineers, pilots, physicians, physical therapists, electricians, and computer programmers apply physics concepts in their daily work. For example, a pilot must understand how wind forces affect a flight path. Okay, that makes sense. A physical therapist must understand how the muscles in the body experience forces as they move and bend. That makes sense. As you will learn in this text, the principles of physics are propelling new, exciting technologies, and these principles are applied in a wide range of careers. Okay, so what's going on here? Talking about modern technologies, talking about how they are relevant to modern careers, modern technical careers, and just up here, sort of talked about Stone Age, Bronze Age, Iron Age, and then it pointed out the MOSFET, the transistor, metal oxide semiconductor, field effect transistor, of which there's more of them than any other object we've ever made. Okay. The underlying order of nature makes science in general, and physics in particular, interesting and enjoyable to study. For example, what do a bag of chips and a car battery have in common? Both contain energy that can be converted to other forms. So a bag of chips has chemical energy, right, in the bonds of the nutrients in the chips, and so does the car battery. The law of conservation of energy, which says that energy can change form but is never lost, ties together such topics as food, calories, batteries, heat, light, and watch springs. Understanding this law makes it easier to learn about the various forms energy takes and how they relate to one another. Apparently unrelated topics are connected through broadly applicable physical laws, permitting an understanding beyond just the memorization of lists of facts. Okay, so it seems to be going on quite a bit here. All right, I'm going to press through. I hope it's not just going to start going in circles. Okay, no, just a little bit more of the opening section. Science consists of theories and laws that are the general truths of nature, as well as the body of knowledge they encompass. I've seen videos about the epistemology of science and like people trying to pin down. All right. People trying to pin down what a scientific theory and a scientific law are in contrast to one another. And a theory is, well, it's like a set of laws, isn't it? And it creates sort of a human understandable story about a situation. I mean, imagine if you had a machine that could just sort of predict what's going to happen in a physical situation, but we humans just had to take the machine's word for it because the language was too complex or something. I don't think in that case we'd say we have a scientific theory for it, but we do have a means for prediction. Scientists are continuously trying to expand this body of knowledge and to perfect the expression of the laws that describe it. Physics, which comes from the Greek physis, meaning nature, is concerned with describing the interactions of energy, matter, space, and time to uncover the fundamental mechanisms that underlie every phenomenon. This concern for describing the basic phenomena in nature essentially defines the scope of physics. Right, so physics is not about, your love life or what it's like to be a bat, something like that. It's connecting these phenomena to each other. Physics aims to understand the world around us at the most basic level. It emphasizes the use of a small number of quantitative laws to do this. Yeah, like that's kind of something that physicists are attracted to, the idea of just compressing it all down onto one piece of paper using small symbols which stand for quantitative objects, whether it's just a simple number or like a package of numbers, like a vector and so on. And those laws which can be useful to other fields, pushing the performance boundaries of existing technologies. Okay, so consider a smartphone. That's a smartphone right there. Physics describes how electricity interacts with the various circuits inside the device. This knowledge helps engineers select the appropriate materials and circuit layouts when building a smartphone. Knowledge of the physics underlying these devices is required to shrink their size or increase their processing speed. Or think about a GPS. Physics describes the relationship between the speed of an object, the distance over which it travels, and the time it takes to travel that distance. GPS relies on precise calculations that account for variations in the Earth's landscapes, the exact distance between orbiting satellites, and even the effect of a complex occurrence of time dilation. Most of these calculations are founded on algorithms developed by Gladys West. Who's that? An American mathematician. There she is. Okay. Born in 1930. She is known for her contribution to the mathematical modeling of the shape of the Earth. It's a whole article about the shape of the Earth. And her work in the development of satellite geodesy models. Okay, what's that? Satellite geodesy is geodesy by means of artificial satellites. Okay, what's geodesy? Geodesy or geodetics is the science of measuring and representing the geometry, gravity, and spatial orientation of the Earth in temporally varying 3D. All right, so in plain words, I think it's about just modeling the shape of the Earth and how to get from point A to point B in an efficient way. I would say so. And then satellite geodesy is using satellites to do that. And then her work in satellite geodesy was incorporated into the GPS, Global Positioning System, which is extremely important technology, just being able to say where you are. And that was attributed to Gladys West. So thank you, Gladys West. Mathematician and computer scientist who programmed the first computers capable of highly accurate remote sensing and positioning. When you use a GPS device, it utilizes these algorithms to recognize where you are and how your position relates to other objects on Earth. Okay, I understand that. Okay. Just a little bit further to go now. Knowledge of physics is useful in everyday situations as well as in non-scientific professions. Okay, this paragraph was overdue, right? Not only it can't just be important to physicists and technologists, but also to others. It can help you understand how microwave ovens work and why they're not going to kill you, for example. Why metals should not be put into them, and why they might affect pacemakers. So it's extremely practical in that sense as it surrounds us. Physics allows you to understand the hazards of radiation rationally and more easily. It also explains the reason why a black car radiator helps remove heat from the engine and why a white roof helps keep the inside of a house cool. Similarly, the operation of a car's ignition system, as well as the transmission of electrical signals throughout our body's nervous system, are much easier to understand when you think of them in terms of basic physics. Okay, good. So that's making it relevant to people who aren't physicists or don't want to be involved with that. Just everyday, regular people. And now it's going to connect it to other disciplines, isn't it? Okay. Physics is a key element of many important disciplines and contributes directly to others. Chemistry, for example, since it deals with the interactions of atoms and molecules, has close ties to atomic and molecular physics. And a lot of people will just say, well, you know, chemistry can be reduced to physics, and I don't buy that, but I understand. Most branches of engineering are concerned with designing new technologies, processes, or structures with constraints set by the laws of physics. That's true. In architecture, physics is at the heart of structural stability and is involved in acoustics, heating, lighting, and the cooling of buildings. Yes, it is. I'm surprised they haven't mentioned optics. Parts of geology rely heavily on physics, such as radioactive dating of rocks, earthquake analysis, and heat transfer within the Earth. And then you get hybrid disciplines, biophysics, geophysics. That's combining physics with other disciplines. Okay, in closing here, we're going to connect it with biology. And then that's the closing section there. Physics has many applications in the biological sciences. On the microscopic level, it helps describe the properties of cells and their environments. On the macroscopic level, it explains the heat, work, and power associated with the human body and its various organic organ systems. Okay, so let's think. It can be used to explain why you can't get a human-sized beetle, for example, or a beetle-sized human. That's one connection it can have. Let's see. It is not necessary to study all applications of physics formally. What is most useful is knowing the basic laws of physics and developing skills in the analytical methods for applying them. The study of physics can improve your problem-solving skills. Furthermore, physics retains the most basic aspects of science, so it is used by all the sciences, and the study of physics makes other sciences easier to understand. Okay, understood. Now, before looking at the scale of physics, we're going to put a pin there and come back to it. Because now I'm going to be looking at chemistry. Your alarm goes off, and after hitting snooze once or twice, you pry yourself out of bed. You make a cup of coffee to help you get going, and then you shower, get dressed, eat breakfast, and check your phone for messages. On your way to school, you stop to fill your car's gas tank, almost making you late for the first day of chemistry class. Welcome to class. Why should we study chemistry? Do you have an answer? It fulfills an academic requirement, but if you consider your daily activities, you might find chemistry interesting for other reasons. Most everything you do and encounter during your day involves chemistry. Making coffee, cooking eggs, and toasting bread, they all involve chemistry. The products you use, like soap and shampoo, the fabrics you wear, the electronics that keep you connected to the world, your world, the gasoline that propels your car, all these and more involve chemical substances and processes. Whether you are aware or not, chemistry is part of your everyday world. Oh boy, can't wait to see. Chemistry in context. Throughout human history, people have tried to convert matter into more useful forms. That's true. Our Stone Age ancestors chipped pieces of flint into useful tools and carved wood into statues and toys. These endeavors involved changing the shape of a substance without changing the substance itself. But as our knowledge increased, humans began to change the composition of the substances as well. Clay was converted into pottery. Hides were cured to make garments. Copper ores were transformed into copper tools and weapons. And grain was made into bread. So there we have food, weapons, ornaments mentioned, yeah, and clothing. So it's relevant right from the very start. Humans began to practice chemistry when they learn to control fire and use it to cook, make pottery, and smelt metals. So this is saying that it's not some brand new thing that's just made up whole cloth. It's been with us since the beginning. Subsequently, they began to separate and use specific components of matter. A variety of drugs such as aloe, myrrh, and opium were isolated from plants. Dyes such as indigo and Tyrian purple were extracted from plant and animal matter. Metals were combined to form alloys. For example, copper and tin were mixed together to make bronze, and more elaborate smelting techniques produced iron. Alkalis were extracted from ashes, and soaps were prepared by combining these alkalis with fats. Alcohol was produced by fermentation and purified by distillation. Attempts to understand the behavior of matter extend back for more than 2,500 years. As early as the 6th century BC, Greek philosophers discussed a system in which water was the basis of all things. You may have heard the Greek postulate that matter consists of 4 elements: earth, air, fire, and water. Subsequently, an amalgamation of chemical technologies and philosophical speculations was spread from Egypt, China, and the Eastern Mediterranean by alchemists who endeavored to transform quote-unquote base metals such as lead into quote-unquote noble metals like gold, and to create elixirs to cure disease and extend life. Phew. Okay, a little bit worn out at this point. Right, that was great. Just having I keep trying new stuff for science. Keep trying. Might stick with this, not sure. But the point is to just keep trying until I find something that works for this channel. Be well.